In this last video for week 2, we will look at the options for loss functions for different classes of problems, specifically classification, regression, and semantic segmentation. Let's start by recapping what makes a good loss function. The purpose of a loss function is to quantify how well our model is performing for the specific problem at hand. But while several functions might do this, like accuracy for classification, they are not all suited to being loss functions, since if we are to find our way to the global minima by taking small steps in the gradient, then what we want is a loss function which is smooth and differentiable, and as far as possible, robust to noise and outliers. Therefore, in the first lecture, we looked at use of cross-entropy for classification, which we saw was convex for a single neuron at least, and also it offered advantages in that it had a large range sufficient to distinguish clearly between very wrong and slightly wrong answers. We looked at the binary form, for which the final activation function needs to be a sigmoid to squash the output in the range 0 to 1. And the multiclass form, where the multiclass entropy is a weighted sum of logs of the predictions, for which only one term will be 0 for each example, since there is only one class for which the true label yj will be 1 and not 0. And in this case, we need to swap out the sigmoid for its multiclass form, the softmax. This will return a vector of predictions f, following a probability distribution which sums to 1. An alternative loss for classification is the hinge loss, which is related to the max margin loss of support vector machines. For the binary case, this is given by the following, such that when yi and zi have the same sign, which will indicate the correct prediction, and zi is greater than or equal to 1, then li will equal 0, as in that case 1 minus yi times zi will be less than 0. On the other hand, when they have opposite sign, or the magnitude of zi is less than 1, suggesting the prediction isn't confident, then the loss will be linear with zi. So in this way, the loss is seeking to maximize a margin by penalizing predictions not only when they're incorrect, but even when they're correct but not confident. Moving on to regression losses, some commonly used examples include the L1 or mean absolute error loss, where here these lines indicate calculation of the modulus or the absolute value. The L1 loss is typically robust to outliers, but as we saw in the first week, technically this modulus function is non-differentiable at 0. In practice, however, this is just fixed during optimization and seen for gradients of value. An alternative is the mean square error. So this is good as it's strongly convex and penalizes big errors much more than smaller ones. However, as a result, this makes it very sensitive to outliers, which can be a problem. Another option, therefore, is the smooth L1 or Huber loss, which is a piecewise function which effectively implements squared or L2 loss for small errors and L1 loss elsewhere. Here, alpha tunes the user's definition of small, so in PyTorch this is set by default to 1. Further, in Barron et al., which is linked at the bottom here, a generalized regression loss was proposed, which for different values of alpha reduced two different types of loss, including L2 for alpha equals 2 and a pseudo-Huber, or smooth L1 for alpha equals 1, where in his CVPR talk where he introduced this concept, Barron demonstrated the limitations of L2 effectively with the following animations. So specifically for data with low noise, L2 works quite well, as shown here on the left. However, for this example with a cluster of outliers, optimization results in a poor intermediate solution with much poorer convergence. So the loss ends up being much higher, and you can see that the fit is very poor. It's intermediate to these two groups. In these circumstances, a smooth L1 or Huber-like loss can really help, where you can hopefully see that the end result is a function which fits to the main trend in the data and ignores the outliers left out here in the loss plot. So these have high loss, but the overall loss is much lower. Moving on to semantic segmentation losses, The goal of semantic segmentation is to assign every location in an image a label, so it's like per pixel classification, and accordingly cross-entropy is a perfectly valid loss. You do, however, see alternatives based on dice overlap, where these particularly come into their own when classes are highly imbalanced. At a high level, cross-entropy has better behaved gradients, but overlap-based losses can be really useful where the goal is not to miss detection of important but very small objects like lung nodules for lung cancer or focal lesions in the brain. To understand these, we first need to define dice overlap, which is estimated from twice the intersection of two sets of points, x and y, i.e. all points which have a common label, normalized by the total size or number of pixels or voxels in each region. On its own, dice overlap is not suitable as a loss in the sense that it calculates similarity rather than dissimilarity, and so would need to be maximized instead of minimized. Thus, to make it a loss, what we need to do is subtract the overlap from 1. Then, the practical implementation for binary dice overlap works in the following way. We sum over the ground truth times the predicted labels y hat, where these have been hard thresholded to return a 1 or 0. So this combination here is therefore 1 if both yi and y hat are 1, otherwise it's 0. Thus it counts all locations where the class is 1 in both images. The denominator then normalizes through by the total number of voxels or pixels with class 1 in both images. Note, for the binary form, we don't need to consider the 0 class, as if the foreground class overlaps and the background class completely overlaps, and the epsilon here is just to avoid nans occurring through division by 0. Writing the dice in this form allows for estimation of the gradient using the quotient rule of differentiation. However, one can instead consider probabilistic predictions f of z rather than the hard thresholded ones y hat. To do this, we must also consider the 0 class, which is shown here. Doing so creates a smoother loss and therefore smoother training. Dice losses may straightforwardly be extended to consider multiple classes, as well as be extended to weight certain classes more heavily than others. For example, this is the generalized dice loss proposed by Carol Soudre in 2017. Here, the prediction is summed over a total of k classes, and a weighting is added, which is equal to 1 over the total number of locations for that particular class. So this is therefore going to upweight classes with few examples. This is particularly important if the dataset is highly imbalanced, but generally it is important to be aware that dice or overlap is always biased by region size. If your data is imbalanced in any way, it's going to be easier to reduce the loss by fixing larger regions than smaller ones due to the fact that the coefficient is normalized by region size. Other examples include the Tversky loss for binary segmentation problems. This weights false negatives far higher than false positives. In other words, for lesion segmentation, where it's more important not to miss any lesions than it is to over-segment a bit, it will consider it much worse if you label any lesion location as background than if you label some background as lesion. The parameter alpha here tunes the weighting towards false positives, and the parameter beta tunes the weighting towards false negatives. The generalized Wasserstein loss then goes further to take into account between class relationships to balance misclassifications which are semantically more acceptable against those that aren't. In other words, there will be problems where some wrong answers are more wrong than others. For example, it may be less bad to misclassify a voxel as belonging to a tissue that's known to border the true class, and in these cases it may be possible to encode these relationships through a decision tree as shown here for brain tumour segmentation, where the necrotic core of a tumour is known to be surrounded by what is known as an enhancing core, and then the non-enhancing core, and then edema or fluid. So we don't expect to see the necrotic core bordered by edema. These relationships can be used to encode per pixel per label weightings. Finally, two last options we will look at are the sensitivity and specificity loss, which is very close to the Tversky loss. So this supports tuning a balance between sensitivity, which seeks not to miss any of the foreground, with specificity, which focuses on the background. In other words, it trades off making sure to capture your lesions against over-segmentation again. After all, if you label every voxel in the image as lesion, you certainly wouldn't miss capturing all the lesions, but also it would be just as uninformative as not segmenting anything at all. Finally, weighted cross-entropy is a weighted form of cross-entropy that can also allow preference for certain classes. So that gives you quite a lot of options to choose from, and there are many more available through PyTorch which you can check out here. Here are some examples of how we've used them in the notebooks. So here we pass no arguments, and this is how we've created them. And here is an example of where they're applied in the following way, passing the true labels and the predicted ones which come out of the forward pass. While we're talking about these, however, I just wanted to make note that the default PyTorch cross-entropy allows you to supply a weights tensor should you want to apply weighted cross-entropy. So it's expecting this weights tensor to be a 1D tensor with a weight per class. It also supports both binary and multi-class entropy, where in the latter case you need to pass it one hot encoded ground truth labels. Here are some of the regression losses, the ones that we've discussed today. You won't need to change from the default parameter values in most cases, with the possible exception of the smooth L1 or the Huber loss, where here their beta corresponds to the variable that we defined as alpha in these slides. Dice loss, however, is not actually supported by torch.nn. You will be able to find implementations online, but equally you might want to simply define it for yourself. In these cases, bespoke losses may be defined by creating classes which inherit from nn.module, making sure to take into account the constraints that we've discussed in the lectures with respect to making sure that your implementation is differentiable. More details on doing this are defined in this link here. So in summary, when choosing a loss for deep learning optimization, there are several important things to consider. First, what is your problem? Is it classification or is it regression? These require different choices for loss function, as the first one seeks to predict categories, and the last one, regression, involves prediction of continuous numbers, and therefore is more suited to distance measures. Secondly, do you have noisy or imbalanced classes? If you expect outliers, you need a loss which is robust to this. If the data is imbalanced, the loss may need to be weighted. Thirdly, if you're defining a loss for yourself, is the implementation that you've made differentiable? Have you chosen a smooth function? Is it robust to noise? In this video lecture, we looked at several different types of loss for classification, regression, and segmentation problems, including cross-entropy, which is suited to classification and segmentation, hinge loss, which can be used for classification. We looked at L1 and L2 and the smooth L1 for regression, and we considered variants of dice loss for segmentation. This should cover the main bases and suit a broad range of problems. However, you may come across questions that require bespoke losses or combinations of losses, in which case you may need to define your own. So that's it now for week 2. Please finish by completing the Keats quiz, and I will see you in the live session.